Okay, so here's the first of I don't know how many videos I'll be making for um, homework 3. So this is covering the sections 2.1 through 2.3, which is about limits. um, so yeah, I just kind of looked at the online homework and I just sort of picked out some problems that I think people might need a little bit more guidance with. And I tried to make up similar problems. So first, we see some problems about secant lines and slopes. So there's nothing really special about a secant line. It's just a line between 2 points. Um, Typically, we call it a secant line if it's a line that's in between 2 points that's on another graph. Um, so for this example, we are going to find some slopes of secant lines, and it's going to be the secant line between this particular point and Q, and Q is going to actually be several different points. P is always going to be this point, but we're going to consider several points Q. Um, Specifically, Q is going to be a point on this graph, y equals x cubed, and I'm going to give you several different x coordinates. It's going to be all of these x coordinates. Um, so, yeah, let me just, so I showed the work on the first one. So here's how we do this. It's just the slope of a line between 2 points, and we know how to do that. It's rise over run. One of the points, of course, is P. The other point is Q, where Q has, for this example, Q has this x coordinate, so I just put 1.1 here. To find the y coordinate of Q, I just use this. It's y equals x cubed. So I went ahead and I went in a calculator and I did 1.1 cubed, and it gave me that number. So I just wrote it down. So that's all I did there. And then what I want to put here is the slope, and it's the slope between this point and this point. So again, I do rise over run. I subtract the y coordinate, so I took the y coordinate of this minus the y coordinate of this, and I'm dividing it by, and on the bottom I subtract the x coordinate, so I do the x coordinate of this minus the x coordinate of this. And I used a calculator again, and this told me 3.31, so that's how I got that. And I didn't show the rest of the work, but that's also how I got the rest of these. It's just using different x coordinates. In general, to get Q, you do the same exact procedure. The x coordinate of Q is going to be whatever the x coordinate is given. So actually, maybe I can, for this video, I can fill in the work for this one. Q is 1.01, and then if I do that cubed, because I'm so good, I can do this in my head, I would get that. So to find the slope, again, it's just I subtract the y coordinates. So 1.030301 minus 1 over 1.01 minus 1. And that should give me that answer. And that's how you do all of these. Of course, the decimals get a little bit ugly, but it's not that bad. So, all right. So that's nothing too complicated. It's just some terminology and then finding some slopes of lines. Why are we doing this? Because what we're really getting at is tangent lines. Now, a secant line is like a line that goes through 2 points on the graph. So here, by the way, this is the graph of y equals x cubed. It's the same curve we were talking about up here. And here is the point 1, 1. And I've drawn a sketch of the tangent line. So while the secant line goes through 2 points, the slopes that we found is like going through this point and maybe another point that's chosen nearby, and we just find the line through those 2 points. The tangent line is supposed to just come in and just barely touch the curve at just 1 point. And the way you find a tangent line is, and well, we haven't really formally defined the concept of limit yet, but it's a limit. What you do is you take a secant line. Of course, a secant line is through 2 points, so you choose this as one of your points, and you choose the other point somewhere very nearby. And then you take that second point to be closer and closer to the first point until they're essentially the same point. That's how you get the tangent line. So this is going to be more formal later, but for now, let's just make a guess. Can we guess the slope and the equation of this tangent line? And I'm going to make this guess based on the table that we filled out. So, like I was saying, to find the slope of the tangent line, I'm going to take the slope of the secant line, which was this, x cubed minus 1 over x minus 1, and I am going to take x close, super duper close to 1. In other words, the limit as x goes to 1. And based on the table, we can make a guess as to what this is. And let me emphasize that for right now, this is just a guess. But let me ask you the following. If x gets closer and closer to 1, what does it look like the slope is getting close to? And if you think about the values of x that we plugged in a few values that were bigger than 1, and like this is 1.1 is pretty close to 1, but it's not that close. And then this is closer, and then this is closer. We also plugged in some values that are smaller than 1, because when I say close to 1, it's not really specifying bigger or smaller. You can be very close to 1 and bigger than 1, or you can be very close and smaller than 1. So down here are some values that are very close to 1 but smaller, and 0.9 is kind of close but not that close. And then this is closer, and then this is closer. If you look at what happens to the slope, as I get closer and closer to 1, this number seems to be getting closer and closer to 3, right? And if you want to fill in more parts of the table, like if you want to try 1.0001, you'll find a slope that's even closer to 3. Similarly down here, like these slopes are smaller than 3, but they're getting closer and closer to 3. Like this one's 2.997. That's very close to 3. And again, you can, if you want to fill out more rows of the table and do like 0.9999, then you'll find a slope that's even closer to 3 than this. So in the end, we're not going to find limits using tables. This table is just, let me emphasize, it's just a way for us to make a guess. It's a pretty educated guess, but we're going to find more formal ways to do this. But for right now, based on what I see in the table, I would have to guess that the limit of these slopes is 3, because it really looks like the closer x gets to 1, the closer the slope gets to 3. And it looks like it's getting extremely close. So let's say that's 3, and let's say that's the slope of the tangent line. So let's say that's the slope. And then to do the equation of the tangent line, I can just use the point slope form of a line. So this is where you know a point that it goes through, and we do know a point that this goes through. It goes through the point 1, 1, and it has a slope of 3. So that's the equation of the tangent line. Okay. Then I see in the online homework there's some sort of conceptual questions about what do limits mean. So let me just put this out there. If I say limit as x goes to a of f of x equals L, what that means is f of x can be made, we say, arbitrarily close. And when I say arbitrarily close, I mean as close as we like to L by taking x close enough to A. Let me say that again. So what does this mean, as close as we like? What this means is you can tell me how close you want it to be. Like you can tell me how close f of x needs to be to L. And you can tell me as close as you want. You can say it needs to be within 0.1 or 0.01 or 0.00001, and no matter what you say, no matter what closeness you want, I can tell you, well, as long as x is close enough to A, where I get to say, okay, the difference between x and A has to be as close as I say, and I get to name whatever number I like 0.1 or 0.0001 or whatever I like. And as long as I'm able to tell you that as long as x is that close to A, then f of x is going to be as close as you wanted it to be to L. And as long as I'm always able to do that, we say the limit as x goes to A is, of f of x is L. Now, there's an important thing to emphasize about this. When I say x is close enough to A, we don't care what happens when x is exactly equal to A. We only care what happens when x is very, very close, but not exactly the same as A. So, in particular, if I say the limit of as x goes to A of f of x equals L, that doesn't necessarily mean that f of A equals L. That doesn't necessarily mean that if I plug in where x is exactly A, that I will get exactly L. And it doesn't even mean that f of A would be anywhere near L. It might be very far from L. F of A could even be undefined. So this statement has nothing to do with what happens when x equals A. It only matters when x is close to A, but not the same as A. So I tried to illustrate this in these two pictures. So here's two graphs, and I just labeled this A and this L. So in this situation, I would say that the limit as x goes to A of f of x is L, because if I look at values that are close to A, like here's values on the x-axis that are close to A, if I follow those up to the graph, it looks like the y-coordinate is close to L. Here's a picture that's basically the same thing, except I drew an open dot here. So the way I drew this picture, f of A is not even defined. But still, if I look at the values that are close to A, but not exactly A, and I follow them up to the graph, they're all close to this point. I could also fill in this, or I could also draw a dot, like maybe down here. And now that I've changed it, f of a is defined, but it's not L. F of a is whatever this point is, and L is up here. And still, I would say that the limit as x goes to a of f of x is L. I'm just trying to emphasize the point here that in this picture, the limit as x goes to a of f of x is L, and that has nothing to do with what happens when x is exactly a. This dot could be completely open with nothing, or it could be a closed dot somewhere else, or it could be a closed dot right here. And in all of these cases, we say that the limit as x goes to a of f of x is L. Okay. Why is it blurry? Okay, there we go. All right, so let me also say a word about what we call left-sided and right-sided limits. So when we write just a standard limit like this one, we have to consider values of x that are both bigger than a and smaller than a. When we write this, all that matters is that x is supposed to be what we say close to a, and close to a could mean a little bit bigger or a little bit smaller. In contrast, when we talk about left-sided limits and right-sided limits, we only consider, for left-sided limits, we only consider x a little bit smaller than a, and for right-sided limits, we only consider values of x that are a little bit bigger than a. So this is like, x is still close to a, but this is now specifying which side of a it's on, whether it's smaller or bigger. So here I drew a graph, and in this picture, the limit as x goes to 1 from the left, and we write this minus like above the 1 to emphasize that this is a limit from the left. Of f of x is 1 because of this. Well, maybe I shouldn't point exactly at that point, but it's because of the values that are a little bit to the left of 1. If I look at 1 and then I go just a tiny bit to the left and go up to the graph, I find that I'm very close to this point. So as x approaches 1 from the left, the graph is approaching this point. And this is a y-coordinate of 1, so that's why that's 1. Meanwhile, if I approach 1 from the right, so maybe I'll put my pen here and I'll slowly move it towards 1. So this is approaching 1 from the right. If I were to trace the graph, like I'll do that again, but I'll go up here, I find myself approaching this point. And this is an open dot, like there isn't actually a point exactly here, but as I move to the right, I'm nevertheless approaching that point. So I would say the limit as x goes to 1 from the right is 3. By the way, if I were to ask you for the limit as x goes to 1 just as a standard limit, so this is not specifying a side. I have not put a minus here or a plus here. We would say that limit does not exist because, well, it's because if I don't know which side x is on, then I don't really know whether I'm approaching this point or this point. There isn't really a specific number that f of x is approaching if I don't know which side x is on, whether it's up to the left of 1 or to the right of 1. So we would say that this is my abbreviation for does not exist. And that can happen with limits. Not every limit exists. So this would be a limit that does not exist. In fact, this limit would only exist if the left limit and the right limit were the same. So that's one way to evaluate a limit. If you're able to do the left limit and the right limit and you find that they're the same, then this limit is also the same number. Otherwise, if these aren't the same, then this one doesn't exist. And just for fun, I decided to put down one more piece of information. Of course, we've been talking about what's the limit as x goes to 1. So I just thought it might be good to say what if x is exactly 1. F of 1 is just 1, and again, that is because of this point. This point is filled in. This is an open dot, so the graph is actually here, so f of 1 is this point, which is 1. Okay, so so I'm over 20 minutes, so let me start another video.